All right, so let me just go back to where I finished last time. In fact, let me go back one more slides. I presented this SDP relaxation for the distance geometry problem, and I told you how to choose or a few ways to choose this matrix F. Now, what happens if the your SDP formulation is too large for the solver? Because this is the problem with SDP solvers. There's a technological bottleneck. They work very well, okay, and we have better and better solvers as time passes, but it's still much better to use an LP solver instead. So how can we solve an SDP using an LP solver? Well, one way to do that, and I learned this trick from my friend Amir Ali Ahmadi, is to use a diagonally dominant matrix constraint instead of a positive semi-definite matrix constraint. Why? Because diagonally dominant matrices are all positive semi-definite, okay? And vice versa, this doesn't work. So in fact, the approximation, the inner approximation of the PSD cone that I'm going to present now is, as I said, inner. So you may, this means that you no longer have a relaxation. Well, you don't have a relaxation of the SDP. Okay, so what is a diagonally dominant matrix? It has this property. For every row, let's say row, these are squared matrix, and they matrices, and they're symmetrics. For every row I less than n, the diagonal element is greater than or equal to the sum of the absolute values of the other elements in the row. Okay, so this is an example of a diagonally dominant matrix. If you take, for example, this row and you sum up the absolute values of all these things, you don't reach 1. Okay, so that's what it means. Strong diagonals. Okay, so how do we show that diagonally dominant matrices are SDP? The proof goes through an important theorem that is called Gersh-Göring's circle theorem, okay? And the theorem itself says this: if A is symmetric n by n, and for all I less than n, you define Ri, this kind of, this quantity here, the sum of off-diagonal absolute values of entries, then you define the interval I, big I as the diagonal entry minus Ri and the diagonal entry plus Ri. Okay, if you do all this, then every eigenvalue of the matrix A is in some interval big I indexed by I. Okay. All right. So this is the proof. I'm not going to go through the proof, but it's a nice proof, in fact. So you're welcome to read it when I share the slides at the end of this talk. Let me just point out that at this point, if you believe this theorem, it's obvious then that a diagonally dominant matrix is going to be SDP, because this is the definition of a diagonally dominant matrix, okay? And this is precisely R, okay? And so we know now that I minus Ri is greater than or equal to 0, which means that every eigenvalue has to be in a diagonal, in an interval II, and this interval, every endpoints of these intervals are greater than 0, okay? So the eigenvalues in particular are going to be greater than or equal to 0, which means that A is PSD. All right, so this is the constraint that we need to impose over our LP in order for the LP to be a diagonally dominant programming kind of entity, meaning that if we want to say the matrix of decision variables X is into the set of diagonally dominant matrices, we have to impose this constraint. This constraint is not linear, okay, because of the absolute values here, but it's close enough. In particular, there's an easy reformulation to linearity by introducing an additional matrix variable T, okay, still n by n and symmetric, and then you can replace this nonlinear term, which is the absolute value of the matrix big X. You write it as T, okay, so you replace it with T, and then this becomes this, okay, just by replacement. And then you have to add these sandwich-like constraints, okay, that essentially imply this. Okay, together these two linear constraints will imply the constraint star. Okay, so instead of adding the definition of diagonal dominance, you can add these two linear constraints, and lo and behold, you obtain an LP. Okay, so this is what we had. This is the crucial linearization of the distance geometry constraints, where everything has been, the original system would say xi minus xj equals dij squared. Okay, this is the original system, and we linearized it to this form here. And now we're saying that x needs to be diagonally dominant. Okay, and so in order to do that, we turn this problematic or slightly problematic constraint into these two linear constraints, and we have an LP. Now this LP still doesn't have an objective function, but you can add the same objective functions that I talked about before. We'll talk about that later. Now let me tell you what the issue is with these inner approximations. So suppose now that our so we call these constraints the linear constraints, ax equals b. Okay, so these are ax. This is the feasible set defined by ax equals b. Okay, and then we want to intersect it with the diagonally dominant matrices cone, and this is a representation, a silly representation of the DDP cone. Okay, now you can see that this does not, these two sets don't meet each other. Okay, so the DDP could be infeasible even though the original SDP was not infeasible. This is consistent with the fact that DDP is, well, diagonally dominant matrices are an inner approximation of the SDP, the PSD cone. Okay, so what can we do? Well, if we use the push and pull objective, I'll remind you that this came from a maximization of the sum over all the edges, ij, xi minus xj squared, and this would pull xi and xj apart, and then the constraint would be for every ij in the edges, xi minus xj squared less than or equal to dij squared. Okay, so and this would push them apart. Okay, so if we linearize all of these things, we come up with something like this in the constraints, but the reversed sign, and for the objective, we simply maximize this form. Okay, so that was the push and pull SDP relaxation. In the case of diagonal dominance, we can also reverse. Instead of saying less than or equal to and max, we can say greater than or equal to and min. This doesn't change much when we've got a linearization like an SDP or a PSD, because it doesn't impact on convexity of these constraints. Okay, they're all linear. Okay, so it doesn't matter what side you look at them at. All right. So instead of writing this constraint, we're going to relax it to this constraint to make this set, this blue set, larger, and hoping that there'll be some intersection. Okay, and now we use the objective with a minimum in order to try and balance the fact that we've relaxed the equations. Okay, so this is what happens. And now we do find some feasibility. This is not a guarantee. I'm just saying we do, in the sense that if you compute with a few instances, you'll convince yourself that at least for the distance geometry problem applied to proteins, very often you get a valid solution, a feasible solution. I don't have a theoretical result that says that it's always the case with proteins or anything like that. Okay, so this is the Ddp formulation for the distance geometry problem. Essentially, it's just this three constraints that are saying x is in Dd. Okay. All right, so let's see what happens now if we look at dual cones. A set C is a cone if for any two elements of the cone, the affine combinations of the two elements is again in the cone, okay? And if C is a cone, the dual cone to this cone is called C star, and this C star is composed of all the elements that make, taken as vectors, making acute angles in a certain sense with all the elements of C. This is what's really saying acute angles. Of course, this inner product does not need to be interpreted as a Euclidean entity, but let's just by analogy say that these defines acute angles, okay? So picture a cone and picture all of the things, all of the other vectors that make acute angles. Whoops. As I was saying, picture a cone, and then everything that makes acute angles, like this and like this. Okay, this would be the dual cone. So this thing. All right. Now, C, okay, is a set of matrices here. Okay, so instead of having to deal with an inner product in a Euclidean space, we use the Frobenius product. Okay, where I remind you, it's the trace of Y transpose X. Okay. And now one more notion, an n times n matrix cone C is finitely generated by a set of vectors. Okay, so matrices are finitely generated by vectors if there exists a set calligraphic X of vectors, okay, such that for all elements of the cone, there is a sequence of coefficients, non-negative coefficients, so that X can be written as an affine combination, a conic combination, in fact, of the rank 1 matrices obtained by writing the vectors in outer product form. So these would be column vectors. You would have XL here. That's one element here in the sum, and that's multiplied like this by XL transpose. Okay, and so this is like an n times n matrix with rank 1. Okay, so finitely generated means by vectors, it means that this element can be written as a non-negative linear combination of rank 1 matrices out of the vectors in the generating set. And now we look at how we represent the diagonally dominant cone. Okay, so a possible representation is always, well, a representation is, many representations are possible, but a representation in this form is possible here because we've seen that the diagonally dominant cone is in fact a polyhedral cone. Okay, it can be written as an LP. Okay, so we can ask ourselves, well, we can take the extreme rays of the cone. Okay, and then if we find the extreme rays of the cone, they will be certainly in finite numbers. So their set calligraphic X will have this property, okay? Because then if we have the extreme rays of a cone, every element in the cone can be a non-negative linear combination of those, okay? It remains to be seen whether the extreme rays are rank 1 matrices, but we'll see that they are. In fact, it was shown by Barker and Carlson in 1975 that these matrices were the extreme rays of the DD matrices. So this epsilon 0 or big calligraphic E0 would be the set of all of these matrices EII, and that's basically the matrix where there is just a 1 over a diagonal. Okay, so there's 0, 0, and then 1, and then zeros everywhere and everywhere else. These are the EIs. Okay, and then the others, EIJ plus and EIJ minus, they have a minor made of 1s and 0s elsewhere. So for example, if I show you an example of EIJ minus, it could be, I don't know, 1 and then -1 here, -1 here, 1 here, and then zeros elsewhere, zeros elsewhere, zeros, 0, 0, 0 elsewhere. Okay, so that's the kind of matrix that EIJ really is. Okay, so these actually these matrices generate our extreme rays of the DD cone. Okay, and you can write them as they are all rank 1 matrices. I don't know if you can see it with your naked eye, but if you can't, then take the standard basis of Rn and verify that for any element of the standard basis, big EII is EI times EI transpose, and big EIJ plus or minus is EI plus or minus EJ times EI plus or minus IJ transpose. Okay. So not only we found the extreme elements of DD, but we can also express them as rank 1. Well, they are rank 1 matrices. Okay, so if C, now this is this theorem is about the representation of the dual cone. Okay, so by definition we said that the dual cone is this. Okay, and this theorem states that we can actually write this Frobenius product as we can restrict it to the rank 1 matrices in the finite generating set. Okay, so if C is finitely generated by X, then the dual cone has a representation in terms of the finite generating set and not only of the whole cone. Okay, so this allows you to write the dual cone in terms of a finite set of matrices, which are all rank 1. And instead of going through the proof again, I will let you look at it later if you're interested. This proof is very simple. In fact, it should be a two-liner, but I wanted to be extremely clear. Okay,
Leo.
Yes.
Could you just tell us what S is again? It's on the previous slide. Y is an S. N.
So Sn is a set of all symmetric matrices of order n. So this is saying that Y is a symmetric matrix of order n. Okay.
Thank you.
Okay.
Leo, I have a question.
Yes.
So the DD cone is approximating the semi-definite cone.
Yes.
An inner approximation.
Yes.
So do you have some idea on how good an approximation it is? Does it deteriorate as n gets larger?
No, I don't have an idea about this. I have some experience, some computational experience. And that computational experience doesn't seem to suggest this fact, but the computational experience is not a theorem, and it's only limited in my case to instances that come from protein folding. So I wouldn't know. Pablo, do you know?
Yeah, so some things are known, like and I mean it really depends on somehow what parts of the cone you're looking at. But like, kind of, I think there are some results that kind of say that in the limit, right? Kind of then essentially any kind of polyhedral approximation will be a very small part of the PSD cone. I mean,
okay.
In the limit in a certain sense, but this is regardless of this specific approximation.
Okay, thank you. All right. So I presented all this material because I wanted to actually write down the constraints of that would define the dual cone in an explicit form that I was able to pass to a solver. Okay. So now I have this representation. Okay. And this representation is limited to a finite set of elements, set of objects. I will remind you that this representation can also be written in this more familiar form. These are the constraints I want. Okay. So if this is for a general cone, a general finitely generated cone. Okay. If I look at DD star, okay, now I can show finally that DD star contains the PSD cone. So if X is a PSD matrix, okay, then by definition for every V in Rn, this holds, okay? Vxv is greater than or equal to 0. So certainly, if it is true for all V in Rn, it must certainly be valid for the V's in the finite generating set of DD star. So in this case, this shows us that PSD is a subset of DD star. So we have this picture. We have the PSD cone, and then somehow DD star, okay? And then this is PSD, and inside PSD, we have DD. this is the picture that we have. All right. So if in general, even if you apply it to another dual cone, if the generating set is polynomially sized, you get a compact formulation because you only need add these constraints to determine the membership to the cone, to the dual cone. If you have an exponentially large set, you can use column generation. But in the case of XDD, in fact, you have a number n squared of extreme rays, okay, as this result by Barker and Carson shows. So you can actually add them all in a compact way. Okay, so this would be the formulation that you look for every V in XDD. This is still not very practical. It is not, okay, so, okay, so questions are being asked, but luckily my chair is answering them. Excellent. So this is DD. So this is still not a nice form if you want to use a language in practice like ample or something like this. So in fact, you can notice, well, if you think about it for a while, you will see that this constraints for these kind of elements, and these kind of elements, we know them because I'll remind you, they are standard basis elements combined to make rank 1 matrices. Okay, so if you work them out, you will see that these corresponds to EII, and these corresponds to E minus IJ, and these corresponds to E plus IJ. Okay, and here I really should have for all I less than j, like in this case, but I observe that here we already added these parts. And so, well, this, of course, they imply greater than or equal to. And so I only need to add those that are not in E, okay? So in the end, this, oops. In the end, this formulation here only needs to be complemented by these cuts, and that's a dual DDP. Okay, so that's a dual DDP formulation for the distance geometry problem. What are its computational properties? Well, first of all, no, theoretical properties, very easy. The SDP relaxes the original problem, and the dual DDP now relaxes the SDP. So this also relaxes the original problem, which is not the case for the inner DDP formulation. Okay, this is an outer DDP formulation. It incredibly yields extremely tight objective function bounds with respect to the SDP, not with respect to the original problem. But if you work out, I've observed this in two cases: the distance geometry problem, and also the alternating current optimal power flow problem. The dual DDP formulations in these two cases give extremely tight bounds of the objective function with respect to the SDP relaxation. So they are tight. On the other hand, the solutions, so this is about the optimal objective function value, but the solutions, the optima themselves, they may have a very large negative rank. So typically, the sum of the positive eigenvalues is more or less the same than the sum of the negative eigenvalues in the solutions, okay? So that's bad because you can't really seem to hit the PSD cone. So you get a good solution value, a good objective function value, but the solutions themselves, they are very far from the PSD cone. At a certain point, I even tried something like, this is the SDP cone, and this is the dual DD cone, and this is the DD cone, okay? And I tried to pick a solution here and the optimal solution here, and I tried to do bisection over this segment, but it weirdly didn't work at all, meaning that I was moving very close to one of the 2 points and stopping. So this segment lies in a weird subspace with respect to the SDP cone. It's almost as if this segment were sort of almost parallel to, I know it doesn't make sense because the SDP cone is not exactly polyhedral, but this is what I got out of the experiment. So it was an inconclusive experiment. Okay. All right, so let's move to one crucial issue at this point. We've worked with matrix formulations of the DGP, and every time we have obtained an n times n matrix. Okay. However, we were looking for an n times k matrix. Okay, with k less than n, and in fact, k would be a choice. We would be given k. All right. Meaning that we can't just accept the k output by the algorithm. We want a definite k. For example, k equals 2, two-dimensional representations. K equals 3, three-dimensional representations of graphs. Okay, so there is this discrepancy. How do we deal with it? Well, one way to deal with it is to lose dimensions. Okay, and because I already told you about principal component analysis as a way to lose dimensions, well, let's use it. Okay, so the SDP or the inner DDP will yield PSD matrices. Okay, of course, the inner DDP may fail to be feasible, but suppose it is, like in my experiments with proteins, then you need to lower this n down to k. Okay, and I recalled you that the PSD matrices are also gram matrices of something. Okay, so you can apply PCA to the solution and then keep the k largest components of PCA and get a solution x prime, which is n times big K. Okay, so this is now in the correct dimensional space, but it has errors. One way that I found was extremely expedient and extremely fast, in fact. Well, not extremely fast, but sufficiently fast, that would fix most of these errors for at least small, medium-sized, and some largish instance, was to use x prime as a starting point for a local NLP solver deployed on some positional variable formulation. Okay, we've seen a few of these. I've shown one before, the push and pull formulation, but then there was also the quartic form, the unconstrained quartic, where you have xi minus xj minus dij squared, all squared. So you can use also this. So any of these formulations will work. With a local NLP solver, you can also give it some limited amount of time if you don't want to waste too much time during the refinement phase, but it will improve this x prime considerably. So you'll get something, you'll get an x star, which is usually quite a good solution. Okay, and it beats using an exponential time algorithm to solve a problem globally. All right, so let's see a different type of dimensional reduction strategy. This is based on concentration of measure. Bervinix made this, well, this is not Bervinix's invention, but he explains concentration of measure in his 1997 paper as follows. The value of a well-behaved function at a random point of a big probability space X is very close to the mean value of the function, okay? And so the probability of hitting something that is far away from the mean behavior of your space, of your phenomenon, is low. Okay, so this is the important point. All right, so for example, if you apply it to a Lipschitz function, this is the definition of a Lipschitz function f, Lipschitz function f. There is concentration of measure if there exist constants c, small c and big C, such that for every epsilon greater than 0, the probability of sampling an X that is far away from the expected value of f is small and decreases very rapidly towards 0. Okay? So the discrepancy from the mean is unlikely in this sense. This sense is unfortunately hardly workable in practice. Well, it's perfectly well defined theoretically, but if you want to extract a recipe for computation, you are blocked by the lack of knowledge of these constants. You have to guess them. All right, so Bervinix theorem says this. When Bervinix theorem and algorithm, I should say, because he presents this as his naive algorithm. In fact, it's naive because it consists of 3 assignments with no ifs and no loops. It's an extremely simple algorithm. Okay, so we consider manifolds calligraphic xk for each k less than m, with m being bounded above by a polynomial in n the number of variables. Okay, so these manifolds contain contain points that are over these quadratic surfaces, okay? And the problem it addresses is to decide feasibility of the following set, whether the intersection of all of these manifolds is empty or not. And let's say find also a solution, find a certificate, or find something that is close to a certificate in this case. All right, so if you write the STP relaxation of these sets, you get these linear equations now in the matrix variable big X, okay? And you need to say that big X is PSD. And if you solve this STP, you'll get a solution X bar, okay? The algorithm is as follows. You factor X bar, which you can do because this is positive semi-definite, with one of the factors that you call T, okay? What you do is you sample a random vector from a normal distribution in 0, 1, component-wise. Each component is sampled from a normal distribution with mean 0 and variance 1. And then you set X prime equals to T times Y, all right? So Bervinix proves that this concentration measure occurs here, this kind of statement. So there exists a universal constant C and an N0 integer, such that for every larger integers N, the probability that the distance between this solution that you found with Bervinix naive algorithm and each of the manifolds is bounded above by this function that increases with N, but very, very slowly. Okay, and the probability of this happening is 0.9. Now, this 0.9 is not a magic number. There is a proof, and you can change this 0.9, trading it off, for example, this N0, so that it becomes smaller or larger. So this really, there's probably a version of the theorem that you can write as something like greater than 1 minus epsilon to the minus something. Okay, so this is a way to present a result that in fact is in concentrational measure spirit. It's something that has this shape. Okay. So what is the algorithmic application of finding an X prime, which is in a lower dimensional space? So remember that this X bar was N times N, and X prime is now in a vector in Rn, okay? So if we were using our STP relaxation to lift a problem that was hard in N dimensions, and now in N times N dimensions, it's easier, it's more linear, let's say, then we have a problem of retrieving an original solution like we did in the DGP before. So if X prime is close to each of the manifolds, we can try a local descent from X prime and have reasonable hope of finding a feasible point in the intersection of the manifolds, okay? So that's the principle behind the fact that I'm finding that the refinement phase, i.e. apply a local NLP solver to a dimensionally reduced version of an STP solution, was giving me good performance. However, let's go back to Bervinix naive algorithm. So the formula itself is complicated to parse, okay? But I'm going to try and give you the origin of each of the terms. Okay, well, the distance, so you can understand the distance, this would be the Euclidean distance, so the projection of X prime over the manifold, okay? So the projection, the segment between X prime and the projection of X prime over this manifold. Now, the rest of the formula, this was the universal constant, so we can't really control that. This part arises because of T, okay? Do you remember that T was a factor of X bar, okay? So if you just take norms, the norm of T would be the square root of the norm of X bar. And this other term arises from concentration of measure. In order to apply this to the distance geometry problem, there is an added difficulty, i.e., we don't have vectors in Rn, we have matrices in Rkn, or rather n times k, as I said before. Okay, so this is the difference. And it so happens that we couldn't really apply, well, there are two ways to look at the extension of this result to our case. One way would be to stack these matrices. So instead of having Kn, you would stack them and get something like Nk, okay? So this would be the first column, and this would be the second column, and this would be the third column, for example. If you do this, yeah, then you can apply Bervinix naive algorithm to these kind of vectors. But then your N raises a lot, okay? So it increases a lot. So this is not good for computation. So in order to address this problem, we reproved the whole set of statements leading to Bervinix result with his consultancy and sometimes his help, might I say. So thank you, Alex. We reproved it for this case, okay? So y here, instead of being one-dimensional, okay, sorry, a vector in in n dimensions. So instead of being a vector, it's now an n times k matrix, but you have to adjust the standard deviation to 1 over square root of k. Okay, so Bervinix theorem works in rank k as well. I'll skip on the proof structure. So the heuristic that I'm using here is solve an SDP relaxation of the DGP or also a DDP relaxation, get a solution x bar, and then factor x bar, sample y as a k times n matrix, and then x prime would be t times y. Okay, and now do the refinement phase. Use x prime as a starting point for a local NLP solver on, for example, the quartic formulation. And this returns the improved solution x. So this worked very well. So to give a summary to this long section of my tutorial about distance geometry, well, about the distance geometry problem and NP formulations for it. First of all, try the non-convex formulations in position variables. If your instance is well solved by that, then be happy with it. If these quadratic non-convex or quartic formulations are too hard, then solve an SDP relaxation and try and lose dimensions. If the SDP relaxation is too large, then solve a DDP approximation, okay? Then whatever you do between these two things, you have to lose dimensions, and you can do this with either PCA or Bervinix naive algorithm. And whatever you do, then at the end, you refine with the local NLP solver. Okay, so this is a process that served me well for distance geometry and also for the alternating current optimal power flow problem. So it seems to be more general than just distance geometry. In fact, it's probably good to apply it to any QCQP. Now, let me move to another section, which may well be the last. I don't know if I'm going to have time to do this part. So we talked about losing dimensions. Let me briefly talk about random projections, okay? So these are also based on concentration of measure, but the argument is different than the one given in Bervinix naive algorithm. So the gist of this of these random projections is as follows. Imagine that you have a matrix, big A, the blue matrix, and this contains in columns, okay, each column is very high dimensional. Say, for example, this is the matrix representation of a database of movies. It's YouTube, okay? So each movie has been standardized in size and in length so that it occupies the same size. Maybe some columns have been padded with zeros, it doesn't matter. Anyway, this contains these movies, okay? So you must imagine a very tall matrix A, but it could also be reasonably fat, meaning that, you know, YouTube may have movies that occupy, I don't know, 1 gig of RAM, okay, of space, of storage, so 1 billion bytes. On the other hand, they won't have 1 billion movies, but probably they have millions of movies. I don't know how many movies they have, but they have a lot of movies. So this matrix A is really humongous, okay? And if you want to do something like cluster the columns of this matrix A according to similarity of the vectors, you're out of luck, because even the most efficient ways of clustering vectors are going to be very slow on this huge matrix, okay? So what you can do instead, if your method for clustering is based on Euclidean distances, such as, for example, k-means, is to pre-multiply A by this matrix T, which is short and fat and normally sampled component-wise, okay? So this would be in A would be M times N, okay? So it would be in M rows and N columns, and that means that this green matrix should be M columns and K rows, okay? And K must be much smaller than M, okay? All right. So the insurance that this pre-multiplication carries with it is that for every pair of columns of the blue matrix, the Euclidean distance is more or less the same as the Euclidean distance between the projected version of the matrix A. And this happens WAP. What does WAP mean? Well, WAP means with arbitrarily high probability, okay? And it shows something that we've seen before briefly in Bervinix naive algorithm. And it describes a set of events, a sequence of events EK that depends on some parameter K, where the probability approaches 1 exponentially fast as X increases, i.e. the probability of EK has this kind of behavior, okay? So the Johnson-Lindeschow lemma encodes more formally what I just presented in the gist of random projections. Given a set of vectors A in Rm with n vectors and an epsilon greater than 0, there is a k that is greater than some constant over epsilon squared times logarithm of n, and a k times m matrix T that has the required property. And the approximation that I gave here is now more explicitly made out as an epsilon approximation that is multiplicative in nature, okay? So these are all two norms. Okay, so this happens if T is sample component-wise from this distribution. Remark the similarity with the Bervinix sampling, okay? So the proof essentially aims at showing that the probability that A and TA, these are sets of points in high dimensions and in low dimensions, are approximately congruent in this sense. This is the approximately congruent sense with some positive probability, whence the proof infers by the probabilistic method that such a T really exists. Okay. So in practice, if you want to use this, there's the usual safeguards against using theorems that really cannot be made into recipes because they rest on certain universal constants that you don't see here, but I assure you that, okay, you see one here, and then there's another one in this exponent there. So you don't know, you never know the values of this constant, so you can never really follow the theorem in a computationally precise or theoretically precise sort of way. However, you can still derive, so you can still treat it as a principal reassurance. Okay, you do what the theorem is telling you to do, and you don't know whether it'll work in your case, but you rest assured that there's many cases or infinitely many cases where it works. Okay, so the probability that A and TA are approximately congruent is positive, in particular greater or equal to 1 over n. So in theory, this probability can be made arbitrarily high by simply resampling sufficiently many times. Okay, but every time you resample, you would have to ascertain whether the distance geometry, the Euclidean distance matrix of A and the Euclidean distance matrix of TA are really similar, okay? And so these computations cost a lot, which you don't want to do. So in fact, you have to sample very few times. What I do is I sample only once. Why does this work? This works because in fact, it's very easy to show this result, okay? So on average, the distances will be equal, okay, on average, okay? And then the concentration of measure result tells you that the probability of error decreases exponentially fast. So you can read this to mean and this is actually what happens in practice, is that if you sample only once, you'll have some probability of getting some pairs wrong, okay? So for some very few pairs into this set A, okay, we'll have a very different distances, okay, but very few, and all of the rest will basically verify this relationship. And so if this happens in a big database, you can understand a big set of data is going to be noisy and incomplete and wrong anyway. So no, YouTube will not have all perfect pixels of every perfect film. There will be films where the voice is somewhat crackling. So there will be some imperfections in any large data set. So the fact that this method might fail to preserve certain very few of the pairwise distances shouldn't hurt any method too much. Of course, it may hurt a method very much on a given instance, okay? Maybe some given instances will be very wrong, but that's very unlikely, okay? So this is why you can sample T just once, essentially. The other surprising fact of this method is that K, the target dimension, the lower dimension, is independent of the original number of dimensions. It only depends on the number of vectors, logarithm of n, and on your epsilon. Okay, so that's surprising. The original dimension that you thought was exactly right for describing your data, in fact, has no bearing up to epsilon precision and up to the fact that you want to preserve Euclidean distances. By way of an example, I can exhibit what Google Images used to do, or still does maybe. If you launch a query such as spaghetti code here, you can find at the top line a sort of set of cluster representatives. Okay, so this clustering was made apparently instantaneously. Okay, and there will be some pre-computations, of course, but not for every query. So what they may do, and I don't know whether this is exactly what they do, but what they may do is that they could transform all of these after having found the pictures for a query. They may project all of the vectors. All of these images can be encoded into vectors. They may project all of the vectors down, first of all, to a common size and to a small size. And then on those vectors, they can run a clustering, okay, like k-means, for example. Based on those clustering, they can choose their representatives here, and that has to be really fast. So I tried this, and these are the original images. And if I did the clustering on the original images, it took me 0.4 seconds, and it gave me this clustering. But if I projected down the images, then I obtained exactly the same clustering in a fraction of the time. So that kind of works, okay? I don't always get the same clustering, of course. I was lucky there, but you can get maybe you can get permutations of this clustering, of course. That's entirely possible, but you can recognize that it's a permutation. On the other hand, you might find a really different clustering with a small probability, hopefully. Okay. Right. So let me skip this this slide. In fact, I just want to attract your attention, but not talk about the fact that you can apply random projection to mathematical programming formulations. And I've worked out how to project linear programming, semi-definite programming, and quadratic programming up to a certain extent. Okay, so you can look up these references. I'm not going to use them in this talk. All right. So distance instability. This is something that I found really amazing. Okay, so I discovered this when I was giving a talk, and I was complaining that k-means was really unstable. And then a PhD student in the audience told me maybe it's distance instability, and I said, "What is it?" And she didn't explain. She gave me a reference, and then I went and saw. Sorry, this is not the reference. I'll tell you later. Okay, so but now I'm explaining it to you. Consider the k-nearest neighbor algorithm. Okay. So essentially, you have a bunch of points, many points in Rn, and you have a distance function, and you have a selected point z, okay? And this is separate from the points. Now, the problem is to find the closest point and the furthest point, for example, okay? That's not exactly the KNN problem, but never mind. This is the problem that we're going to look at. And of course, getting the closest point, not the furthest, but getting the closest point or the closest K, the K closest points in a data set is used in a lot of problems in data science, including K-means. All right, so you can interpret this setting of finding the closest point or the K closest points. In this case, let's just look at one the closest point. You can reinterpret this setting as with random variables. Okay, so these points are not points anymore; they are sampled from a distribution. Okay, and these distributions can be multi-dimensional, so they are vectors of random variables. And this is another distribution. Let's say that all the points share the same distribution and they are independent. This can be any distribution. The Z can be any distribution. Whatever you choose and whatever the distribution, you can then define the distance to the closest point and the distance to the furthest point also as random variables because they are functions of these two random variables. Okay, so that's the min and that's the max. Whatever it is, everything is a random variable here. The selected point is a random variable. All of the points are random variables. The distance, the minimum distance to the closest point is a random variable. The maximum distance to the farthest point is a random variable. Okay, if you interpret it this way, the distance instability theorem tells you that essentially if these distances behave reasonably well, then closest and furthest point are at about the same distance, which is really, really, really bad. Okay, so it means that in high dimensions, let's say that m goes to infinity, that's really the dimension. Okay, so it doesn't need to be the dimension, but you can interpret it to be the dimension. If as you go up the dimensions, you are no longer really able to distinguish closest from furthest point in Euclidean distances. Okay, that's a tragedy for a lot of algorithms, and it's a tragedy for our dream of mastering large data. It's the bane of big data much more than the bane of dimensions or the curse of dimension. This is the more precise form. The variance of this quantity has to be 0 in the limit as the dimensions go to infinity. And this is the conclusion, the limit for m goes to infinity, for the probability of the maximum distance away from your selected point being within an epsilon of the minimum distance to the closest point is 1. Okay, so this is the real tragedy, and this is the reference that explains it. So again, I won't have time to go into proofs, but the proof is very easy. There is nothing weird. Okay, there's just elementary statistics. What you must understand is that this result does not apply to points, it applies to distributions. So if you have a set of points, a definite set of points, and maybe it's orderly, and it doesn't really come from any distribution that you won't know of, but from processes that are very orderly, this may not apply to your set of points, okay? But when does it apply? Well, it applies to independently identically distributed random variables from any distribution. It also applies with particular forms of correlation that you can read more about in the paper. It applies when the variance tends to 0 also, and more. Especially this is bad. The computational experiments with k-means made by the authors showed that instability already kicks in with n greater than 15 dimensions. We don't need to go into the millions of dimensions. 15 dimensions is already bad. What are we going to do? So these are my experiments that led me to complain about k-means and prompted the student in the audience to tell me about distance instability. I don't know if you can distinguish the colors, but here I'm using mauve and green. And according to the starting point, k-means would say whatever it wanted. Okay, so there would be, this is in 100 dimensions. There is not a single run that gives me a coherent cluster. There's also cases where it doesn't apply. You can see that these are quite evident cases, complete linear dependence on all distributions. And then, of course, the dimensions are not 1 billion or 15, but it's just 1. So also, if query points is approximately the data point, then it doesn't apply. Anyway, so implicitly low dimensionality, order. So in these cases, it may not apply. Okay. But when I tested it for 3 distributions, uniform, normal, and exponential, okay, so these are the dimensions, okay, up to k dimensions. I sampled a lot of points from 0 to 10,000 dimensions in every case. And this is the epsilon, so the distance, well, the difference between dmin and dmax, okay? So in very few dimensions, because I was sampling, I think, on a sphere, so the distance between dmin and dmax was the epsilon was 1, okay? And then very rapidly, it goes down, down, and then 0, 1, it reaches 0, 1 already in 200 dimensions. As you go along the x-axis, you can see that it goes towards 0, and maybe this epsilon is still just over 0 on a scale that you would think we can recognize, okay? Yes, maybe we can recognize it barely, okay, up to 10,000 dimensions. I don't know about 1,000,000, but let's just assume that we can still recognize the difference between dmin and dmax. But in order to run k-means, we don't need the difference between dmin and dmax. We need to tell apart the closest from the second closest, the closest from the third closest. Okay, so these are very important differences. And if already the closest to the farthest requires an epsilon of 0.001, do you really think that you're going to be able to recognize the closest from the second closest in I don't know, in 1,000, 1,000,000, 2,000,000 points, 1,000,000,000 points? That's unlikely. So that's a limit of Euclidean distances, not only Euclidean, in fact, distances, let's say, that have that property of regularity that I showed before. So it generates algorithmic instability. Now, I presented 2 types of results in these last 10 minutes or 20 minutes. One was related to random projections and the other to distance instability. Let's agree to just refer to the Euclidean distance here, okay? Are these results related? Well, just informally. On the one hand, an n-dimensional point cloud big X, like this, with very big dimensionality, by instance instability, you get this, all right? So it seems like all of the useful information is within an epsilon. If T is a random projection, then you can project you can project your vector set down to this number of dimensions at the expense of an epsilon accuracy. So essentially, I'm asking, is really all of the useful information about the distance seem to be enclosed into an epsilon? Otherwise, we wouldn't be able to tell them apart, okay? Are we losing this epsilon when we are projecting down? So this projection that seemed so magic, so useful, is it really useful, or are we just wasting away exactly that epsilon of information that was really made the difference between recognizing the closest and the furthest? Because that's of course the epsilon, the proofs have nothing to do with each other. These epsilon, they are not the same symbol, definitely in the 2 proofs, but there's still a concept here, sort of not a symbol, but some quantity that is very small that is being traded off in the second case. But it's the first case is telling us that it was really important. So is it really the same quantity? Is it really are we throwing away in the random projections all of the epsilons that was useful before in order to recognize points? And on the other hand, if you start with a dimension with a large dimensional point cloud X, and if you project first, okay, because of the epsilon, you can never really project down to less than 15 dimensions. That's impossible. You'll always project down if you've got a small enough epsilon, for example, 1%, you're going to have to multiply by 10,000, okay? Because you have 0.01 squared, okay? And minus to the -2 in the expression for the projected dimension, okay? So when you do this, you're still in an area where distance instability really hits, okay? Because you have so many dimensions anyway. So it seems like even if you want to first decrease the dimensionality, there's this distance instability phenomenon that won't let you go too low. Okay, so I don't know. I've looked for relations like more formal than what I just told you about. I didn't find anything. I don't despair of finding something one day, but let's say that these proofs are different, the epsilons are different, so I don't know how to relate the two results. I don't know if it's possible to relate the two results, but certainly they seem to be talking about the same thing in a way that makes you doubt that this whole business of considering the Euclidean distance something good for high dimensions is entirely doubtful. And that leads me to 5 o'clock, which means that I won't be able to produce any interesting slides for the graph embeddings with an artificial neural network, but then so be it. I'll pass you the slides. Thank you very much for your attention.
Thank you very much, Leo, for a very interesting talk. So I guess let me open the room for questions, the virtual room for questions. Let me ask you a question to break the ice. So one of the things in Johnson-Lindenstrauss, right, that you know, sometimes it's perhaps a bit tricky, is a dependence with epsilon, right? This dependence of 1 over epsilon squared.
Yes.
Right, that you know, kind of typically for if you want to get some reasonable accuracy or high accuracy for some applications, that requires a dimension to be very high, right? The dimension to which you're projecting to.
Yes.
Is that an issue in the applications that you have in mind?
Absolutely. It is a horrible issue. I'm using 20% accuracy at the very best. So I can have just a factor of, what is it, 14 or 0.2. So anyway, so 400. So I am reduced to throwing away a lot of accuracy, and still I'm kind of making it work. Okay, so essentially, my tests have been both good and bad. I have a lot of applications of, for example, linear programming, where these projections really just didn't work. Okay, not at all. And then I had a few selected applications, most of which had dense constraint matrices, where it worked a charm even with an epsilon at 0.2. Okay, so it's hard to say. I could never run anything with an accuracy of 0.01, for example, 1%. On the other hand, most of my tests are about linear programming, which is a very strange application for this, and it required a lot of work, a lot of theoretical work before I could do any experiments. A more direct application would be to have a data set and to project it down. And you can, sometimes your data is naturally at 1 billion of dimensions. And when you project it down to 10,000 dimensions, that's okay. That's really okay. So I don't have all that much experience with projecting raw data, but I know that people are using this. And so somehow there must be something good in it. Maybe not all is stolen, not all benefits are stolen by the distance instability phenomenon.
Yeah, no, because I think it's very interesting whether, you know, kind of somehow, I mean, the theorem guarantees something, right? But, you know, perhaps even more is true, you know, kind of, or perhaps for some of the applications, we don't really need to preserve all pairs like you were mentioning, like, yeah.
I find that all of these theorems that have concentration of measure, they are very, very vague if you want to use them computationally, because all of the possible trade-offs are in the theorem, meaning that you have these constants, the value of which is often unknowable, or at least I can't determine it. And you can use them as gauges. Well, you can, if I make the constant smaller, can I infer what the epsilon should be like, or can I infer something else from the theorem? Sometimes you can play these kind of trade-off games, but mostly it requires some, if you want to do that, it requires some mathematical structure from the underlying application. If you don't have it because you just have a bunch of vectors and you don't know where they come from, then you have to wing it. And that's mostly what I've done. All right, so the dual Ddp formulation looks like a special case of the cutting plane methods for SDP. Possible. The cuts V transpose are extreme rays of the DD cone. Have you tried to improve the relaxation by adding even more cuts from a negative eigenvector? I have tried that, and it got me nowhere because every time I would add the negative vector, the negative eigenvector in that fashion, it would find another solution with Well, I'm talking about the dual DDP here, okay? So it would find another solution with almost the same cost and equally large negative weight. So there seemed to be no end of cuts for some reasons. I don't know. So I tried and then let it go. It's not something that I've pursued.
So if there's more questions, I think you can unmute yourself or you can ask through the chat.
Okay.
Any other comments?
Leo, I've got a quick question. You've got a lot of experience with these protein problems,
Yes.
and this technique of taking the semi-definite programming problem, relaxing to this DDP formulation, and then once you solve, then looking at a local solver to even improve that solution seems to work quite well.
Yes.
What are the properties of the protein problems that make this successful? Have you thought about like what the general properties might be?
Yes, well, I can tell you what some properties of those problems are. First of all, most protein graphs coming from nuclear magnetic resonance, which is the typical kind of experiment that leads to these problems, they end up being rigid or almost rigid. On the other hand, they are never globally rigid. So there's always more than one solution, and these solutions, they are different isomers of the protein. Okay, so most proteins will have a lot of partial reflections at many steps of the backbone. Okay, so there's full of well, there may be, for certain proteins there's more, for certain there are less, but there may be a lot of optimal solutions and a lot of non-optimal but slightly suboptimal solutions that derive from partial reflections, which means that it doesn't really, well, there are more chances of being close to one of these so that the local descent would hit it. Okay, so this is definitely a structure of proteins that is not always the case, for example, in sensor localization or clock synchronization.